Hey all, this is Dr. B. This is just a addition to understanding the difference between PAM sequence divergence and BLOSUM. And my suggestion is to go ahead and read about these scoring systems first. And then once you do that, hopefully this video will help to kind of solidify some of the differences. So a couple things about these. So the PAM system's been around for a long time. It's been used, I think, since the 70s. I believe it was Margaret Dayhoff who did some of the work on identifying some of these mutations in protein families. But basically, the gist of the difference is that PAM, of course, which stands for percent accepted mutation, has to do with the relative amount of mutations per 100 amino acids. And so because of that, the PAM numbers can, are very low and can go very high to about 250. So the word PAM 250 would basically mean that there'd be around 250 mutations per 100 amino acids. And that's a lot. That only coordinates to about a 20% identity overall. And so basically higher PAM numbers are lower identities and lower PAM numbers are high identity. For example, a PAM1 would only be a 1% accepted mutation. So therefore that means two sequences, one PAM apart, have 99% identical residues. And so that's one system that's used, and there's times to use that. And then the other system, again, there's several others, but I'm just comparing these two, is BLOSUM. And BLOSUM basically is the opposite system, that the higher the BLOSUM value, the higher the identity. And generally speaking, the BLOSUM matrix is more of an indicator of the substitution score for replacing one amino acid with any other amino acid. And this matrix is a quantitative approach to determine whether an amino acid substitution is conservative or non-conservative. And so that's really kind of the relative difference between that and a PAM. And that's really useful because, you may say, well, why replace, the Dayhoff matrix? And the answer is, first of all, they had way more data. And number two, it's also a better way of identifying relationships that are distant when you have a much larger amount of data that you can use. And so I guess the question also in this case is, when to use which one? And so that's always a good question. So if you were to not have a lot of information about a sequence, I would think most people would think the BLOSUM 62, and that's a relative number that's used for the particular matrix. You can see that that's this one right here. Is probably the best way to go. It is pretty much the standard for scoring a lot of matrices and is the default matrix that BLAST uses. And so that's why I chose this, because you're familiar with BLAST. And so just again, the relationship between the two, if you have two sequences that are closely related, the BLOSUM matrix would be good. So a higher one, of course, like a BLOSUM 80. And on the converse, you could also use a low PAM matrices, such as PAM1. And so you can see the inverse relationship between the two of these. And then obviously for like a distant related sequence, you would select a low BLOSUM matrices. Because remember, higher BLOSUM is higher identity and lower BLOSUM is lower identity. And therefore also using a higher PAM matrices, such as like a PAM 250. So that's the relative difference between the two of them. So now let's kind of get into a little bit more of the meat of the BLOSUM. So this is the BLOSUM, sometimes called BLOSUM 62 matrix. You can Google it. I mean, it's standard. Sometimes there's another side to it, but you really don't need that. So what you have basically is you have the same amino acids going down as you do across. And so you'll see here that this is the full name, and I know you guys probably haven't had this yet, but these are the symbols for the relative amino acids. So V is valine, and Y is tyrosine, and T W is tryptophan. You get the idea. So really what you're doing is you're scoring a change from one amino acid to another. And I'm not going to tell you yet whether having a high score is good or whether having a low score is good. But let's just kind of see, let's just have a situation where one amino acid doesn't change at all, that you just started off with something and you ended up with the same. So let's do methionine here. So if methionine stays methionine, let me just go ahead and create a little circle here that I can kind of move around. We'll just create this. And then let me get rid of the fill. And then let me make it red. Whoop, didn't want to do that. Sorry about that. All right, so there's methionine, and here's the other M-methionine, and bam, there it is. So you can see that starting off with methionine and having no mutation where you have a methionine, so basically it's an M to an M, so let me do insert. I'll do a little arrow here. We'll just kind of go that way. So an M to an M gives a score of 5, and so that seems pretty good. So now let's just do another one. Let's just say that there is an M to a, whoop, that's wrong, sorry. Let's just say we have a met to a lysine, so that's going to be K is your lysine, there's your met. There we go, that's what I was trying to do. So we can see now we have a situation when a methionine turns into a lysine, and its amino acid is K, we see that that value is a -1. And you're like, huh. So you take this and look and you say, well, if there's no mutation at all, the number's 5. And if there is one, it's a number 1. And if we look across all of these, let's just say, by the way, that the methionine, let's just say, what's a good one to do? Why don't we do glycine? Yeah, there we go. What if the methionine in that position, right here, what if it ended up mutating into a glycine? And we see that that value is a -3. And so you're like, well, I don't get it. Like, I get the M to M. You probably have figured out, based on this, that the higher number is better. And it is. And if you look at a lot of these things, here's a threonine staying to a threonine. That's a 5. And you can see tryptophan, whose symbol is a W, staying to a tryptophan is an 11. So the outside of this, you can tell, is obviously kind of related to the dot matrix. These are, in essence, the highest scores because there is no substitution between any of them. So the higher number is better, but there's difference in the lower number. Like, why are they not both -1? What's the difference? Well, the answer has to do with the structure of the protein and what kind, or the amino acid, and what its characteristics are. For example, like if you were to go from, a point mutation or a missense mutation where you've substituted one amino acid for another amino acid, but that amino acid is also of the same characteristic, maybe say non-polar or whatever, that's not going to be as bad as a more drastic change from one amino acid to an amino acid that has a completely different structure or charge to it. So that would be scored worse. And that's what the BLOSUM matrix is really kind of doing, is at any given spot, it's looking at what these mutations are, and from the addition of whatever your entire sequence is, and where you get these mutations and what the mutations are, you get a relative score. And that's the essence of the BLOSUM matrix and its ability to kind of understand, either evolutionary relationships or mutations through a comparison of one or more sequences. So where does it all come from? What do those individual numbers mean? So what I just did was a simple sequence A and B, and tried to align them as best that I could. And what you'll see here is that there's more than one way that they can align with having the most things aligned. You can see if I do it this way, the T and the A are aligned with the A and the C, and then the T at the end, and we have a different DNA nucleotide here. And I can also try to align it this way, but like which one's right? So if I just use this empty box up here, this is the relationship between why you learned the idea of dot plots and those values to how BLOSUM goes yet a step further, and how PAM does as well. So this should be common space here. You have A, T, C, G, the 4 nucleotides, and you can see every time the same one gets up, we'll just give it a higher score than if there is no match, right? So if we do that, and if we go across and kind of figure out, what kind of score would we get, whether it's aligned or not, if we take the first alignment, we have 1, because it's the same, you can see that it's basically a T to a T, and then another one, which is the A to a, whoops, sorry, let me do the plus sign, another one, and then if I go to do the third one, I have to give it a 0, because you can see that the C to the T is not the same. And the next two also need to get a 0, because not only is C not T, but the T and the G are not, there is no residue alignment for that. So that's going to be plus 0, plus 0, whoops, sorry, plus 0. So I have 1 plus 1 plus 0 plus 0 plus 0. And now if I look, there's another match. That's good, right? There's the A. And then there's the C. So that's another 1. Whoops, there's another 1. This is hard to talk and do this at the same time. And then we have not a match with the C and a space, so that's a 0. And then finally I have the T to the T, T to the T, which is a 1. So when I add all those up, I get 1, 2, 3, 4, I get a score of a 5. So that's for alignment 1. So we're just going to call it A1. That's no big deal. And now if I were to go ahead and do the same for A2 the same way, here's what I would get for my score. I get A1 plus 0 plus 1, whoops, 1 plus 0. Oops, sorry about that. I have to keep hitting the tab every time I do the number, or the plus, but not the number, so it's messing up my brain. So 1 plus 1 plus 0 plus 1 plus 0, and then plus 1, and then plus 0, and then plus 1, and then the T to the T is a plus 1. So I get all those, and I add those up. 1, 2, 3, 4, 6. So basically what this tells me fundamentally is that alignment 2 is the better alignment, simply because there's more in common. And that is kind of like a view of kind of what the BLOSUM is doing, but in a much more specific way than just a 0 or 1. It's taking into account how that amino acid change, and again, this is nucleotide, but it's the relative idea of the same thing, how that amino acid mutation would affect the actual protein itself, because some, obviously missense mutations are worse than others. So hopefully that gave you a little bit of a help about how these work.